Well, good afternoon, everybody. Thanks for coming. For those of you who have been here before, we really appreciate your coming in today, and it's nice to see you all again. For those of you who haven't been here before, welcome. We hope you find this presentation enjoyable and informative. And with that, I'm going to introduce Lee Cook from Capco.
Thank you, Guy.
Take it away.
Good afternoon, everybody. Just a little bit about me before we start, and then I'll have a couple questions about my audience. But Capco Energy Supply, just so you know where I'm coming from, we are a wholesaler of plumbing and heating equipment. We're a single branch. We compete against the Webbs and the Portland Groups of the world, but we really only focus on hydronic heating and cooling, so things that move water around: boilers, pumps, controls, chillers, geothermal equipment, and thermal solar. So our typical customer is a plumber or mechanical contractor that comes in and buys equipment from us. And what sort of separates Capco is our value added in terms of design and technical assistance. We sort of package the control and the mechanical system together for our customers. So that's why someone would come to me versus my competitor. So we don't sell to the public. So on a day-to-day basis, my customer is a plumber or a mechanical contractor. We don't do any potable water, no fixtures, no toilets, no sinks. It's just basically boilers, controls, pumps, valves, and fittings. So if I can get a sense of what my audience is: architects by show of hands, engineers by show of hands, mechanical, electrical, okay. Any contractors? Okay, great. Okay, well, what Guy and Courtney had asked me to go over today is, what today is an efficient boiler room. There are several components that need to be looked at when we talk about how do I upgrade my mechanical system. So we're going to focus today on, if I were going to go and create an efficient boiler room, what are those components? What do they do? How do they affect, their efficiencies? How do they affect fuel consumption? Where's the low-hanging fruit, so to speak? And so we're going to touch on boilers, pumps, and controls are going to be the three primary things. We'll veer off a little bit into some indirect, into some water heating, but I'll let you guys, please, if there's questions about what we're going through, we'll go deeper into it, and we do have about, I think, 45 minutes, and then we'll leave some time for questions at the end. And at the end, I'll show a great little demonstration about variable frequency drive pumping when we're done. We can't really all see it from here, but when we're done, we'll cluster around it, and I'll run you through a demonstration of it, and it really gets the point across about why it's such a great energy saver. So we'll move. Okay, so I've sort of told you about what we're going to try to go over today, and we'll get right into it. What I'm going to, how many people are in boiler rooms on a daily basis or involved in as architects, you're thinking about the mechanical system in terms of the infrastructure in the building. We're going to just get into, what kind of equipment choices should be thought about if this equipment is going to be replaced. So many boiler rooms I go into today, we talk about the life expectancy of equipment being about 20 years old. So often we see 30 years old, 40 years old, and this is what we're walking into: a large cast iron single boiler with in this case, the domestic hot water is going through this tank in the front, and that boiler staying warm all year long to produce that domestic hot water. So there's lots of opportunities for efficiency gain in that type of a strategy. But in its day, it was the state of the art. But so much has changed. This is just an example of if you couldn't do it in one boiler, you did it in several boilers. Very typical mechanical room in an apartment building. Whoever was the hydrotherm salesman was an incredible salesman, because I would say half of the commercial mechanical rooms I go into are these banks of hydrotherm boilers, which were combined multiple flues, multiple supplies and returns to a common header, and I see these all the time. And we'll talk a little bit about how important sizing a system is. Here you can see they've dropped out a couple of boilers, and it's 10, 15 years ago, it's still running fine. So quite often these systems were oversized to begin with. So another opportunity for lots of efficiency savings. If we don't need as big a boiler plant, you don't put in as big a boiler plant. But I see this all the time. So typically there's equipment, the boiler equipment is single stage. It was either on or it was off. We're going to talk about modulating boilers in a minute. Were they the right size? I mean, an effective heat loss and gain calculation is the foundation of any mechanical design. So understanding what you need for a boiler plant is critical. And was it done right? So often you'll have people say, well, there was a million BTUs in there, that's what we're going to replace it with. And that's just not the strategy. That homework needs to be done in the beginning, because you could have had all types of upgrades to the building, windows, insulation. It doesn't need to be that size anymore, even if it needed to be that size to begin with. Standard efficiencies when you chimney vented a piece of equipment were, in this vintage, 70 and 80%. And as the heat exchanger gets coated with, with combustion byproducts, it gets lower. So there's lots of opportunities for savings. Typically it was oil and gas is what you saw. There was no weather responsive control. We'll go into weather responsive control in a minute. And the pumps were single speed. They were on or they were off, and they were sized for that worst day of the year, which is only ever the worst day of the year a fraction of the time. So the rest of the year they're oversized. Sometimes you had boiler or pump redundancy, but usually you didn't. If a piece of equipment was down, the building was down. Today, what's changed is our burners are no longer single speed or one stage, they're modulating. And coupled with outdoor reset or weather responsive control, if we can watch the weather and say, on a 50-degree day, the building only needs 120 degrees of water instead of 180 degrees of water, then let's slow the burner down. So we use that outdoor weather responsive control to modulate the burner. Several ways it's done, but typically you speed up and slow down the fan that brings fuel in, and that's how you speed up and slow down the burner's firing rate. So if we can lower water temperature, for every 3 degrees of water temperature, we can reduce for heating the building. It's about a 1% efficiency gain. So most of the year we're above 30 degrees. So there's a huge opportunity with just changing the boiler to something that modulates to gain huge savings. Obviously, sizing the boiler properly. Don't put in more boiler than you need. You have to obviously have a discussion about redundancy. Do you want how much? If a boiler is down, how much redundancy do you want? So you're typically talking about a couple of boilers to do what the single boiler used to do in the past. There's been a huge gain in efficiencies. We're into there's a lot of claims about efficiency, but when we'll talk about condensing technology, which is above 90%. And as soon as you go above 90%, you really need to understand that the colder the water in the system, the higher your efficiency. And that's just, so you'll see someone claim 96, 97%. Well, it really depends on what the building is using for water temperature. If we've got a high temperature application, baseboard, radiators, fan coils, you're going to be able to have that water temperature low when it's mild out, but on the cold days it's going to be hot, and you're going to be in the 90% range. If you've got a new application where you can have low water temperature, which would be a radiant floor, just think about the larger the surface area, the lower the water temperature. So a radiant floor is a huge surface area, low water temperature. You're sizing a new fan coil unit. You can size a large enough coil to have lower water temperature. You can be condensing all year long, and you start bringing your efficiencies up into the 90s. So we go from 70 and 80s in efficiency with older technology up into the 90s. So there's a huge gain. Modulation gives you a gain. The outdoor weather responsive control gives you a gains. All these gains are what make this new technology so attractive. The other thing that we'll touch on a lot more later is boiler technology has gotten to a point where there's not much more we can squeeze. If we're at 95 and 96%, we don't have huge leaps anymore. We did from 70 to 90, but now we're it's a diminishing marginal return at 94, 95, 96%. Pumping technology is where the huge gains are today. We're going to talk a little bit about that later in terms of going from percentages in the teens to, we can gain 40 and 50 and 60 and even more % savings on our energy consumption and pumping. And controls, now we have the ability to stage boilers, watch the outdoor, watch the temperature, have that boiler ramp up and ramp down, just give enough heat to the space based on the outside temperature, not on to 180 and off, on, off, on, off. So controls have come a long way as well. This is a typical example of that boiler, the big boiler we saw before being replaced by two smaller condensing boilers. Obviously, advantage is you're moving around something the size of a filing cabinet that's 800,000 BTUs. PVC or CPVC vented, and no longer, this technology can no longer go back into the chimney, which we'll talk about in just a minute. We talked about what is modulating. Standard efficiency equipment fired, and it was sized for the worst day of the year. So if it was a 1,000,000 BTU boiler, when it fired, you got 1,000,000 BTUs. Modulating now says if you only need 100,000 BTUs, then we're going to slow our fan down, slow our fuel intake down, and we're going to only give what is needed. So that's really what the term modulating is talking about, speeding up and slowing down that firing rate. Condensing, it's important to understand, in older equipment, condensing was a bad thing. If you had cold water coming back to a boiler, or even worse, a design of cold water, take a building loop, a geothermal heat pump loop that wants 60 or 80 degree water, and you've got a cast iron boiler. You did all this work to protect it, to keep the return water coming back to the boiler above, say, 140 degrees so that there was no condensation, because that flue gas would become acidic when it condensed, and it would destroy the cast iron heat exchanger. Now we actually encourage it. We want to take materials like this that the heat exchanger is made out of, stainless steel, cast aluminum, and we encourage condensation. That change of state from a vapor back to a liquid, just like a sweating glass, there's heat given off in that change of state, and we want to capture that, and that's just what happens. If we can lower the water in a boiler system, cause condensation, we can capture that heat given off in that change of state and put it in the water. So that's why we now can get above 90%, and we actually encourage you to get above 90%. But it takes a different heat exchanger material, one that can take that acidic condensate, and now you've got so little heat left in the flue gas, we can't go back up the chimney. If we put it in the chimney, we wouldn't create much of a draft. We would condense on the sides of the chimney. We would destroy the chimney. So now we vent directly to the outside in a material, PVC, CPVC, polypropylene, stainless steel, depending on the manufacturer, so that we can have condensation in that flue pipe, because it is going to collect there. So that's a big difference. When you hear about condensing boilers, just be thinking venting is an issue, and the material is going to change. So we talked about what is actually happening, but you think about a steam boiler in the past, it did it the other way around. It took a liquid and it had to put enough BTUs into it to boil it. Well, that difference from 212 degrees of water to 212 degrees of vapor takes an enormous amount of energy to lift it up and over that to change state. We're doing the reverse. We're taking that heat by it condensing. So that's a picture of that heat exchanger in action. We are encouraging that to condense. One thing that happens when we talk about this new boiler technology, we go from large mass, large cast iron, lots of water volume. There could be hundreds of gallons in some of these big boilers. And so it was an enormous thermal flywheel. You'd be pumping BTUs and pumping BTUs into this. We do that now with a very small, we might have 2, 3, 4, 5 gallons of water in the boiler at the same amount of BTUs going in. So flow is critical. There's a minimum flow requirement on all this new technology. Well, quite often you may have, so let's take a boiler that has 20 gallons a minute of flow requirement. So it has to be happening. But you've got a system with 30 zone valves and some 3/4 baseboard that might only have 1 gallon a minute per zone or 2 gallons a minute. We need to separate or decouple that boiler from the building loop. And there are devices like this, which are called hydraulic separators, that do that. So along with this new boiler technology comes some of the accessories around the boiler that change. And it's just, you know, this is the things that you'd be looking for in a good design, is when you talk about low mass or small water volume boilers, be thinking about, you know, how do I separate that boiler flow from the system flow? So what sort of happens here is this is a large vessel that's very big, and this is going to and from the boiler, and this is going to and from the system. So the system, and this is a very big volume, air separates very easily here, sediment separates, and this side can have a totally different flow rate as this side, because whatever, it can travel this way, it can travel this way, so you decouple the boiler from the system.
What is that called?
That's called a hydraulic separator.
Is that the same as when we do the injection systems?
Yes, if you, right. So when people, when you look at a boiler drawing, there'll be what they call a close space set of T's. 2 T's close together. Some people will say that's an injection. Or what it does is it is another form of hydraulic separation. It allows you to go around the T a couple of different ways if you have to, but it always gets its flow. The advantage of this is you get 2 more features. You get the air separation and you get sediment separation. If you notice that as you pass that heat exchanger around, its passageways are very small. The passageways of older equipment was very large, and you could have lots of debris moving around, and it would pass through the old boilers. We want to capture that. So we don't want it to go through that passageway and clog that. Then what ends up happening is there's no flow through that. When it's going to boil off in that section, damage that little section of the heat exchanger. So water quality becomes much more important, and those are sort of the things we're learning over the past 10 years about, you know, the unintended consequences of new technology. We put this in, and then we're having to address these other issues, water quality being one of them. People are saying, I never had to worry about, you know, filtering the water and the pH, but now we're dealing with, you know, high-tech metals, we're dealing with smaller passageways, and that's what we have to deal with to get all these efficiencies that we're getting. So this is just an example of sort of what's going on inside that hydraulic separator. And this would be a standard piping design. So this hydraulic separator keeps these guys happy. 1 or 2 boilers running one at one time, both at the same time. A domestic hot water over here allows for both of these boilers' horsepower to work on it, and then off to heating zones. So that's a typical strategy nowadays. This slide is just showing some of the new pump technology. So if you start to see pumps that used to look round like this, of any size, and they start to have a controller attached to it, it's most likely one of the new variable speed pumps. And briefly, this is an example of a building that wanted a redundant pump system. If one pump was down, the other pump came on. So a lot of technology goes into these controllers, where one pump talks to the other pump on a little communication wire, and if one is in error, the other one will come on. If not, they'll just rotate back and forth on a certain amount of runtime. So it's a real nice feature of the new pumps. Another great feature for any of you who have dealt with variable frequency drive pumps in the past, you'd take a traditional pump and you would attach a drive to it, and you'd need to look at some pressure points in the system. So you'd have a kind of in the worst farthest away zone, you'd be looking for a certain amount of differential pressure. So you'd have to put in pressure ports, you'd have to put in a pressure transducer. That would have to give a signal to a drive, and the drive would speed up and slow down the pump motor. Well, this is all, we have this now all in one pump. So you do not need to go back out. It's seeing the pressure differential across its pump. So we don't have to put all that extra work in, and the cost of the pumps has gone down dramatically.
Even the senses, the requirement, the pressure.
Now there'll be no more external drive. There'll be no more pressure transducers in the system. It'll be all built into the pump, and we'll kind of go over that briefly. And I'm not a pump expert. I understand how they work. So what we'll do is we'll go through it. Ask any questions you have about the pumps. Anything that I'm not comfortable with, I'll you leave me your information. I'll get you the answer. But let's move on and just talk a little bit about it. Excuse me. Understanding that this is something that blew me away the first time I really heard about it. If you think about when you see how efficient moving BTUs around with water is versus moving them around with air, it's staggering what the difference is. So let's just do a little example. And this is going to be a traditional pump. Then we'll talk about doing it with a variable speed pump. They're called different things just so you see this. ECM means electronically commutated motor. It's almost synonymous with VFD. You're speeding up and slowing down the pump by changing the watt input to the pump. So if you see VFD, for the most part, or ECM is the true new technology. So if someone says I've got a VFD pump, you can ask, is it an ECM pump? Because that's really what you want to see. If we consider that just moving, yes sir.
What's the electronically something?
Commutated.
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 Excellent.
Electronically commutated, and we'll actually show a slide. Kind of, we'll get into what that means, but not too far. If you consider that 5 gallons a minute of water flow, which is just usually a little bigger than a 3/4 inch, you can get it through a 3/4 inch pipe. We talk about delta T. The temperature the water goes out and the temperature that it is when it comes back is the delta T. That tells us if that temperature drop were 20 degrees and I was moving 5 gallons a minute, I would have given up 50,000 BTUs in the process. Now, we can do that pretty simply with a pump consuming about 32 watts. That is 1,506 BTUs an hour per watt. If you were going to compare that to a typical 4-ton or 48,000 BTU fan coil or blower, it wouldn't be surprising at all to see it taking 1,000 watts to do that. So now you're talking about 1,080 watts to move 48,000 BTUs versus 32. Water's just a great conductor of heat. So when you think about efficient, we accept air movement for other reasons, for cooling, for filtration, for humidification, and it's a very natural tag along to put heat in it because the system's already there. But if you're saying what's the most efficient way, it's moving water around for those BTUs. So we're only getting 44 BTUs a watt versus 1,500. So it's a staggering difference. That's just, and really forget the math part. It's just something that it never dawned on me when you're doing any kind of system design how much more efficient it is to do a heating design water-based, moving water around, as opposed to air-based. It's interesting. Heating systems that are water-based are very forgiving, and the reason for that is as we move, if we're moving a temperature of water around, we can slow it down, and we get almost the same amount of output, going from say 4 gallons a minute to 1 gallon a minute. We drop very little. If we drop temperature, we drop a lot. So the point of that statement is we typically overpump. We size a pump for the worst day of the year. So it's only not oversized for a day or so in terms of hours, 20, 24 hours. The rest of the time it's oversized. And then you could slow a pump down 50 or 60%, and under most conditions, you would never, the people in the space would never tell you it's getting cold in here. So if we look at, let's just look at the a chart that sort of shows that. What we have on the bottom is the percentage of designed flow rate. So this is, someone said, and this is the heat output. So at 100%, we get 100%. But if we drop our flow rate to 80%, we're still about 96, 97% of the heat is still transferred. If we drop all the way to 50% of our flow rate, we're at about 92% of our heat output. So we can, the argument is that these ECM pumps can slow themselves down and still perform. If we can slow it down 50% of our design flow rate and still put out 92% of our heat output, we're saving huge money, because the next thing we're going to talk about is, after this, is the pump affinity law, about how much energy that really is. This is a very typical chart for a piece of baseboard.
Excuse me.
Yes.
The, Are the utilities doing rebates on the ECMs? Taking your regular circulating pump out,
Excuse me.
putting in an ECM?
Yeah, right now, to my understanding, we have under a horsepower, there isn't a program that I'm aware of. There are some pilot programs. You can get some non-prescriptive, if that's the term, some non-prescriptive rebates if you are willing to kind of document it. But my understanding is that they are testing for providing rebates for the smaller pumps.
So that's the electricity side of the equation?
Correct.
Okay.
Yep. So if we look at, anyone who's designed a heating system is used to going right here and saying, okay, if I have a piece of baseboard and I'm going to put 180 degrees of water through it, I'm going to get, at 4 gallons a minute, I'm going to get 610 BTUs a foot. So they'll say, okay, my room needs 6,000 BTUs on that cold day of the year, so I need 10 feet of baseboard. So that, at this, well, if I drop it just to a gallon, so a quarter of this flow rate, I'm still getting 580 BTUs a foot. So we can really affect flow and just barely affect heat output. So that's really the point to get across, because that then tells you why we can slow these pumps down so much and have such incredible savings. I'm missing, let's see if that, oh, there we go. Oh, so someone's good here. So one thing to think about for people designing systems is, we're always asked, you always talk about a 20-degree delta T. Why do you talk about a 20-degree delta T? That's always been kind of the industry standard for designing a hydronic heating system. But if we can slow down the water and still provide the heat, why not do that? So we can talk about larger delta Ts, but what you have to remember is, think about an average water temperature. And a good example of that, if we had a 20-degree delta T, we start out at 180, we come back at 160, our average is 170 degrees. So we should be kind of sizing our heat emitter at 170 degrees. A 10-degree delta T brings our average up a little, but we'll see in a minute what it takes for that pump to have to go and speed up from a 20-degree delta T to a 10-degree delta T. If we went in at 180 degrees, back out at 178, it's an average of, 179 average. If you think about a fan coil unit, it's a great place to have. You've got this big coil and you've got a blower. If you size that at what we call a 20-degree delta T, you're going to have an average water temperature of let's say 170 degrees, 180 in, 160 out. Well, what if we sized that so that we could have a 40-degree delta T and it has to be bigger, its surface area has to be bigger, but if we went and looked at the charts and said, hey, I want 140 degrees of average water temperature to produce the BTUs I need to heat my space. Now, if we went in at 160 and came out at 120 and had a 140-degree average, we could heat our space on the worst day, and we're below that threshold for condensing all the time. So you can take what are traditionally high temperature applications and make them happy to live with a condensing boiler. So that's the idea of, now we've slowed our pump down 2 times, which makes, if we're using this new technology, you'll see how incredibly powerful that is.
So do you go beyond, recommend going beyond 20 degrees?
Certain,
Like to 30 or 35
it
degrees?
depends on the heat emitter, yep. You know, so radiant floors, we typically wouldn't go beyond 20. Some people design for 10 degrees, but that pump has to be, the flow is twice as much, the head is 4 times as much, and the power consumption is cubed. So it's, because it's so forgiving, we can slow the pump down and gain a ton of energy. So that's where we'll end up on the next couple of slides. Induction motors versus the permanent magnet is that ECM motor we talked about. An induction motor is this guy. It's the one you see everywhere with the windings, you know, around the piece of metal that once energized are magnetized. An induction motor has to both energize the rotor and the stator. And if you think about the rotor is the shaft and the stator are what the windings are around, it has to energize them both, and this guy has to try to chase it. So that type of technology, think of both of those have to be energized in order for it to work. If you take a permanent magnet motor, the motor is already, the shaft is already magnetized, so you only have to apply power to the stators. So all of a sudden, you're only powering effectively half the pump. So to do the same amount of work, you do it with half the wattage, and we'll prove that when we look at this display. So this idea of ECM technology is, if we could program with software in the brain the speed that is going around, that magnet is going to chase that positive and negative. It's going to attract and repel that shaft around, and if we could change the watt input, we can speed up and slow down that spinning. And that's really what's happening. Then we just need the technology to do that. So it's when people say, how does it work? You go and program this pump to, let's say, my building is 30 feet of head pressure I need, differential pressure to make the flow work in this building. You're going to program that in. It's then going to calculate based on where this is in relationship to this, and it's watching it all the time. If it's behind it, it says, I got to speed this up to get to where I calculate my duty point. So it adds wattage and it speeds that shaft up. If it says now a bunch of zone valves just closed and I don't need as much flow, I'm getting ahead of the game, then it slows it down. It slows the watt input, lowers it, and the shaft slows down. And that's what's happening all the time in an ECM pump. Now if we look at, this is sort of the predicted savings of that ECM pump over traditional pump technology. In a application where you have changing flow, zone valves that open and close, that is really its sweet spot. 60 to 80% of electrical savings is not hard to achieve if you consider the pump that was sized to run at 2,000 watts on the worst day is running at 2,000 watts all heating season, versus one that only needs to run at 2,000 watts for the 17 or 18 or 20 hours that it needs to. The rest of the time it's something less than that. And this is really the key thing to understand. If your flow rate is proportional to your shaft speed, if you double the flow rate, you square the pressure and you cube the amount of electricity it takes to do that. So people will say, well, do I really need 1-inch pipe? Can I get away with 3/4? You have to think about the effect of what that does to the pump. Your pump may have to get twice as big. And so now go the other direction, slow the pump down by half, you drop the head pressure by the square root, and you drop the watt consumption by the cube root. So so if we look at that, this means that a 2,200 watt motor running at 50% of its rated maximum speed, uses only 13 watts. That's that, you know, the power of that pump affinity law. So anywhere where you're moving water around, be thinking, you know, we've gone in 2 years from 0 ECM pumps to probably 20 or 25% of the pumps that go out are this technology. And within 3 or 4 years, it'll be the only way the pumps will go out.
But a lot of the variable speeds going out are not of that type. Is that correct?
All of the ones that, we're not getting into product, but all the ones that you mentioned are this type.
Right.
They are permanent magnet motored pumps with,
We didn't get these 2 types, so
okay.
I'm sure
So
we got the other model.
This, I guess I'll ask the question, but how many of you are involved in large domestic hot water production? Is that a, you know, we won't spend a lot of time on it, but just quickly, there's technology now where what you used to see was you'd have a large volume of domestic hot water and you'd have a coil in it that carried your boiler water around it. Flip that on its ear and have a large volume of boiler water and a small series of coils of domestic water, and your heat exchange surface area gets gigantic. So as rules of thumb, we always think about, well, 220,000 BTUs is about the most most horsepower I can put into a tank, 120 gallon tank of water. I just can't pump any more through that, and the surface area is not big. Flip that around and you can get about 900,000 BTUs of heat exchange if your vessel is full of boiler water and you've got a series of small copper coils that are carrying your domestic water. And when there's no flow, you're storing almost no domestic water. When there's flow, it runs across the tank and picks up about 100, it can pick up about 100 degrees of temperature rise. So you couple this idea of large thermal boiler water mass with these low mass boilers, and what it solves is the short cycling problem of big, small water volume boilers with lots of BTUs. You might have a million BTU boiler and a 200,000 BTU load, it's going to short cycle, but you give it a 900,000 BTU load and it's going to be happy as can be because it's working on all that water volume. So this is, we talked about that hydraulic separator. This is another great new product that's come out since condensing boilers have come out, and it's a great companion. You can have a tank like this produce 30 gallons a minute of 110 degree water continuously. So it's great for large volume applications. So it's semi-instantaneous is the term if you're asking about it. And this is just an example of 3 traditional gas-fired water heaters with a lot of standby loss and not very efficient burning technology, moving to this idea of you're at the boiler's efficiency rate, 90, 92, 93, 94%, and it's a great, huge producer with very little standby loss. So that's kind of new domestic technology. And I think something we'll then finish up on this, and I'll take questions, and then I'll show you that pump board. But
So go back
Yeah.
on this hot water. So
Yeah.
you're big on this instantaneous strategy. I keep hearing that it's
semi-instantaneous, yeah.
semi-instantaneous, but I keep hearing it's not as reliable.
Yeah, I
very
think
expensive.
the big difference.
And so on.
Yeah. Oh, sure. The question is, the term instantaneous water heater has different connotations. In this example, is it good or bad? We've heard good things and bad things. In this example, we're not actually, there's no combustion going on in this vessel. A lot of instantaneous water heaters are what you would see typically they're wall hung. They have like the Renais, the Bosches, yeah, and they are they don't fire until there's a flow, until there's movement through them. So at about a half a gallon a minute, they then get a call to fire. They burner turns on. It goes through the whole process of starting up. And one of the big complaints is that you get a trailer of lukewarm water, and then you get it comes on, the production is not very good. So there's a lot of mismarketing, in my opinion, because what they'll do is they'll give you sort of the best case scenario. They'll say at 50-degree temperature rise, we produce 10 gallons a minute. And then you don't think that in New England you really need a 75-degree temperature rise in order to get, you know, the water coming in off the street is 40 or 50 degrees, but you want it at 115 or 120. All of a sudden that output that they talked about gets cut in half or gets cut in a third. And I think it leaves a sour taste in a lot of people's mouths. This technology, the combustion is at the boiler, and when you go to draw a little bit of water, it's sitting in a pool of hot water. So there's actually, you can actually draw water through the tank for quite a while before you absorb the BTUs and actually have to turn the boiler on. So there's no kind of sandwiching of hot and cold water. It works very well. So we're big proponents of this, less so of what you think of as the typical instantaneous. There are applications for it, but not that many, in my opinion. Something just to understand, and this, anyone that takes my card, if they want the working version of this, we have an Excel version of this where you can play with the numbers. People are always saying, what's more efficient, electricity, geothermal, oil versus gas versus propane? This little chart puts everything into a million BTUs, which lets you compare them. So you plug in the efficiency, you plug in the unit volume price, and this gives you a per million BTU cost of all the fuels. And if you look today at an example, two most common are natural gas versus fuel oil. And this is pretty current information. A therm of natural gas is 100,000 BTUs, less its efficiency. About $1.25 is a pretty common per therm price right now. And if we look at that against number 2 fuel, people will say, oh, oil's, you know, it's got more heat in a gallon. And that is true. You get about 138,000 BTUs per gallon of oil at $3.60. And most oil equipment is non-condensing. So it's rare to see oil equipment past 86, 87%. There are a few 90s out there, but they're very small. So for the most part, 85, 86% versus the 95, 96% if we're dealing with a condensing boiler in a low water temperature. You convert that over, sort of look at this, $30 a million BTUs for oil, $13.60 for gas. So, and there's I think only been 2 times in the last 6 or 7 years where natural gas, in this example, was more than oil. So it's what's happening with fuel. Propane, which was the one that always surprised me, is even though you can get condensing technology in propane, look at the cost of it if you're up around $3.40 a gallon of propane. It's more expensive than oil. And that always blew me away. I'm thinking it's just it's liquefied, it's gas. And I can get condensing technology, but it's more expensive. Electricity is the wild one. You know, I pay 21 cents a kilowatt hour personally at home. I'll see bills for commercial buildings that are, you know, in this range, but at quote unquote perfect efficiency, look at your cost per million BTUs. A heat pump that has a COP of 3, meaning you're getting 3 times the output per dollar, you know, invested in the fuel, is still, you know, it's good, but it's, you know, natural gas is still less. So there's anything that gave you a 3 COP and you were paying 14 cents, but yeah, 3 COP would usually be ground source. Not when the water temperatures get really cold or really hot, but that's really, you know, you sort of have this, do I want to do geothermal? But you got to kind of think about what are my fuel costs. So is there any, we're pretty much done with that part of the presentation, and I'm happy to answer questions, but I also thought it would be nice to show so maybe I'll take questions and then I'll show you the ECM pump board.
So a quick one on the semi-instantaneous hot water.
Sure.
That's industry standard terminology. You can go Google that and you have a bunch of
Yes.
manufacturers.
And the question is semi-instantaneous an industry standard word? There's only a few manufacturers. The word semi is sort of that's the word that means there's volume of water there. So that's, you'll find.
The liters. You
Sure.
use the liters in the manufacturer.
Yep, absolutely, yep. Yep. Yeah, the instantaneous is what you're used to, is
Yeah,
being,
we don't
yeah,
want the
yeah.
instantaneous.
The semi-instantaneous, yeah, you take my card and I can give you some of the players. We bring this to trade shows, facility shows, just to give people a visual of what's going on. And all we do is, I just have a toggle switch that either powers this pump or powers this pump. And then I move this to so right now I'm taking a typical induction motor, just a permanent split capacitor. It's the pump that we've had for many, many years and that you see all over the place. And this is a residential size. And I'm moving about 6.8 gallons a minute. So we'll call it 7 gallons a minute is what I'm flowing across this system. And this watt meter is telling me I'm using 60 watts to do it. So that's that's sort of the typical hydronic zone of heat. And we're moving what would be about 70,000 BTUs if we were having that 20-degree delta T from supply to return. And it's taking me 61 watts to do it. Now, if I represented some restriction, which would be zone valves closing in the building. That was sort of my worst day of the year. Everything's open. So let's kind of cut the flow rate in half. One thing is you hear velocity noise because it's still trying to pump at its speed, and that's one of the things these get rid of is no need for a pressure bypass valve. Velocity noise goes away. We're down at 4 gallons a minute. Let's get to about 3.5. That's half the zone valves closing. And we're at 55 watts. So we really, we haven't affected the watt consumption of the pump very, very little. And then we'll represent kind of everything closing. Now this pump is still trying to pump. It's generating heat, it has nowhere to dissipate it. 48 watts is what it's capable, that's what it's consuming. And after a short period of time, that pump will burn out if it's what we call deadheading, pushing against nothing. And that happens a lot in buildings where the pump, someone forgets to seasonally turn off the pump and everybody turns their thermostat off and it's just hammering away. So you had to do other things. You had to have spring-loaded bypass valves that could lift up and release some of that pressure, but yet it's still 47 watts. Now let's go back to our worst day of the year, which was 60 watts, and we're going to switch over to this pump doing the exact same work. Now what it does is it's going to speed up and then it's going to slow down, and what I'm setting over here is differential pressure, and whoever's engineering the system will decide what that is, but basically what they're going to do is they're going to look at the flow requirement, and they're going to look at all the piping and all there's friction that takes place as it's moving around, and it's going to say how much differential pressure do I have to create in order to create circulation around this worst circuit. And once that's figured out, it's set here. And in this example, I've got about 5 feet of head is what I need to get and I'm at 7.5 gallons a minute, and I'm at 34 watts and dropping. So the idea of 2 parts of this motor being powered, only 1 part of this motor because I have a permanent magnet that doesn't need power to spin, answers the question. It's at 33 watts versus 60. So we're just about, twice as efficient, and we're doing the same flow. We've got 7.3 gallons a minute. Now the magic takes place when the rest of the year something's off. So let's go to that 3.5 gallons a minute. Now what it'll do is it'll sense that it gets to slow down to keep that 5 feet ahead. Half the valves close off, it sees that change in pressure and it slows down. Now I'm at 3.3 gallons a minute and I'm at 15 watts and dropping. Mm. 14 watts. So we went from 33 watts to 14, dropping half the flow. Now, if we were in a condition of deadheading, we're at 8 watts. So we're less than a night light of energy, and we can dissipate that, 7 watts we can just dissipate off the body of the pump. So you can deadhead a pump like this and never hurt it. And that's a lot of buildings have no end switches coming back to a boiler room, and so how do you turn on the pump, how do you turn on the boiler? You can have this be energized on outdoor temperature. It comes on at 68 and runs until it gets above 68 again, and you're not worried about hurting it. And that's a real benefit.
Do you retrofit old pumps with those controls?
Absolutely. Some of the things that you'd actually retrofit the pump. It'd be a pump replacement.
You change the pump?
Yeah, because you have to have that permanent magnet on the shaft in order to do it. You can retrofit these with a drive, but when you think about the cost of that versus its payback, it's difficult. And not to give any trade price secrets, but the residential version of these, which you're looking at, are about, when they first came out 2 years ago, they were 3 times this guy's cost, 3 times. Payback was pretty 5, 6, 7 years. They've now come to within about 25 to 30% more than this cost. They've really gotten. There's been a competitive race between a couple manufacturers. 115 volt, very easy replacement. Flange spacing exactly the same. They want to be able to swap out old pumps. When you get into the commercial pumps, you're 220 volts, 208, 230 volt range, and you go from about 20 gallons a minute to 200 gallons a minute is the range on the single pumps. And they're very clever. They've taken a volute, which houses the pump, and they've made them into a double volute, single flanges, 2 pumps. And so now you effectively have double the flow, same head, same head it can overcome. So now you've got 400 gallon a minute pumps that don't require any of the hardware. And when we were comparing, if someone said I need 40 gallons a minute of a pump at 20 feet ahead, I would typically size a light commercial pump, and if I compared the cost of the ECM version, I was within 10%. So it wasn't a 2 times the cost or a 3 times the cost. It was almost the same cost for a pump that has phenomenal energy savings. So it's just a no-brainer on the light commercial stuff to put that technology in, and you're not even going out into the system to get it to operate. So anyone and it's what's interesting is there's people just don't know about it yet. It's we're a couple years into it, but it's what we pay attention to.
Are there multiple brands of these?
There are, and there's 2 big players, and they're both European. In what we see mostly now, but everyone's rushing into it. They're either buying, B&G's buying Lang to get that technology, Taco's developing theirs, but this has been European technology for 8, 10 years. So it's, and again, it was always a cost versus, it was an electrical cost or a fuel cost issue is why the technology was so further advanced. They had to get there, but we're able to take advantage of it, and it's. So it's readily available.
Swap out, so the labor involved is small.
Pretty minimal. Yep. You do have to. Yeah.
Go ahead. Lee, I don't want to
Oh,
interrupt you.
are we there?
There's plenty
Yep.
of time for questions. I don't want to stop, but just in the interest of time and for the sake of our presentation, we need
Sure.
to draw this to a close. So I want to thank everybody for coming. I hope you enjoyed our presentation, and please stay tuned for our upcoming events.
Very good. Yeah, I'm happy to answer any more questions.
Yeah.
Great.
It's in my hand.
Thank you.
So we can swap these out in a commercial application without doing